Now we're going to go through a few more examples of use of antiderivatives. Let's say we're in a situation where we know the second derivative of a function. In this case, the second derivative is 6x plus 12x squared. And we know that the first derivative takes a value 3 at 0, and the function takes a value negative 5 at 0. And we want to reconstruct the function from this data. In other words, find f. So this is a pretty classical situation in the sense that when you study motion, what you typically would have is the acceleration. And from that, you want to reconstruct the position function, something that gives you the position at every time so that you can make predictions about the position at time t. In this case, f of 0, f would be the position, f of 0 would be the initial position, f prime of 0 would be the initial velocity. So in this particular case, if we know the second derivative, f prime is an antiderivative of the second derivative. In other words, to get f prime, or at least a general form of f prime, we integrate 6x plus 12x squared in the sense of indefinite integral. And we get 6 times the integral of x, which is x squared over 2, in other words 3x squared, plus 12 times integral of x squared. Integral of x squared is x cubed over 3, so we get 4x cubed. And this is all up to a constant. To find this constant, we use these initial conditions given to us. So in particular, we know that the derivative should take the value 3 at 0. So if we plug x equals 0 in the formula we just have obtained, we get 3 times 0 plus 4 times 0 plus c. So f prime of 0 from this general form is c, and on the other end, f prime of 0 is 3. So we get that c must be 3. That means that f prime is 3x squared plus 4x cubed plus 3. Now f is an antiderivative of f prime, so we integrate this 3x squared plus 4x cubed plus 3, and we obtain x cubed for the antiderivative of 3x squared, x to the fourth for the antiderivative of 4x cubed, and 3x for the antiderivative of 3, and this is all up to a constant d. I introduced a different letter because of course this constant doesn't need to be the same as the constant c. Now to find d, we use this second initial data given to us. The value of the function at 0 is negative 5. If I plug x equals 0 in this general form of the function, I get 0 plus 0 plus 0 plus d. So in other words, f of 0 is d, but f of 0 must be negative 5, so d is negative 5. Putting this together, we obtain that the function f is x cubed plus x to the fourth plus 3x minus 5. Here is a similar problem. Again, we have the second derivative given to us, but the form of the initial data is different. The initial condition now is that we have, instead of having one value of the derivative and one value of the function, we have two different values of the function itself. So we proceed pretty much the same way. F prime is an antiderivative of the second derivative, so f prime, to get the general form of f prime, we integrate 6x plus 6. We get 3x squared plus 6x up to some constant c. And to find this constant c, we can, we cannot find it exactly at this time because we don't have an initial condition for f prime. So what we do instead is find the general form of f, which is an antiderivative of f prime. So f is an antiderivative of 3x squared plus cx plus c, where c is some constant that is to be determined later. Antiderivative of 3x squared is x cubed, of 6x is 3x squared, and of the constant c is c times x. This antiderivative is up to some other constant d, so the general form of f is x cubed plus 3x squared plus cx plus d. Now we're going to use our initial conditions. We know that the function takes a value 4 at 0, so if I plug x equals 0 in this general form, I get 0 plus c times 0, so all this is 0 plus d. So that gives me that f of 0 must be d, if I plug 0 in the general form, and on the other hand, f of 0 must be 4, because this is given to us. Therefore, d must be 4. On the other hand, we know that the function takes the value 3 at 1. So if I plug x equal 1 in the general form, I get 1 cubed, that's 1, plus 3 times 1, so that gives me 4, plus c times 1, plus d, which is 4. In other words, f of 1 is 8 plus c. But on the other hand, f of 1 must be 3, so 8 plus c is equal to 3. Solving for c, we obtain that c must be -5. Plugging the values that we have found for c and d, we obtain that f of x is exactly the function x cubed plus 3x squared minus 5x plus 4. Let's turn to a more concrete situation. A stone is dropped from the CN tower, which is 450 meters high. And first we want to find the distance of the stone to the ground t seconds later, given that the acceleration from gravity is -9.8 meters per second squared. So what we have is the acceleration from gravity. Because the stone is just dropped, the stone is subjected to only one force, which is its weight. And therefore, the acceleration for motion is only the acceleration from gravity. So we have constant acceleration. The velocity is an antiderivative of the acceleration. Acceleration is rate of change of velocity, so the velocity at time t is given by an antiderivative of this constant -9.8. In other words, the velocity at time t is just -9.8 multiplied by t, where t is the time in seconds, and that's up to some constant. To find this constant, we use the initial condition. In this case, the stone is dropped from the CN tower. In other words, it is initially at time t equals 0. When it is dropped without initial velocity. So the velocity at time t equals 0 is 0. And of course, if I plug t equals 0 in the general form, I get -9.8 times 0 plus c, in other words, just c. So that means that c has to be 0, and therefore the velocity function is -9.8 times t, where t is the time in seconds, and that's in meters per second. Now, what we're looking for is the distance from the ground, in other words, the position. Distance from the ground is one way to measure the position of the stone at time t, and its rate of change is the velocity. In other words, the position is an antiderivative of the velocity. So to obtain its general form, we're going to integrate what we have obtained for v of t, and so we get -9.8 times t squared over 2 up to some constant. To find the constant, we look at the initial position. At time t equals 0, the distance from the ground is 450 meters. And on the other hand, if I plug t equals 0 in the general form, I get 0 for the first term, and that's just d. So that means that for time t equals 0, the distance to the ground is d, and is 450, so d is 450. That gives us that the distance to the ground at time t is 450 minus 4.9 t squared, and that's measured in meters, and t is the time measured in seconds. The second question is, how long does it take for the stone to reach the ground? Reaching the ground means the distance to the ground is 0. In other words, we want to know for what t is the position s of t equal to 0. So we set s of t equal to 0, and that means 450 minus 4.9 t squared is 0, which means t squared is 450 over 4.9, or in other words, t is square root of 450 divided by 4.9. Formally, it should be plus or minus square root, but here clearly we start from an initial time of t equals 0, and then time flows positively, so we are not interested in negative time. So in this case, we obtain approximately 9.6 seconds until impact with the ground. In the third question, we want to know with what velocity does the stone strike the ground. And because we know at what time after how many seconds the stone hits the ground, and we know that the velocity at a given time is given by negative 9.8 times this number of seconds. We just plug this value, root of 450 divided by 4.9, inside our velocity function, and we obtain negative 93.9 meters per second approximately. Now, how fast is that? Maybe you're not that familiar with meter per second. Recall that 1 mile is 1609 meters, and of course 1 hour is 60 minutes, each minute is 60 seconds, therefore this is 3600 seconds. That means that if the speed of the stone is that it covers 93.9 meters each second, that means in an hour it's going to cover 3600 times more, and that's in meters. But then to convert it in mile, you have to divide by 1609 meters, because there is 1609 meters in 1 mile. So that gives us velocity of negative 210 miles per hour. The fact that the velocity is negative is simply because we measured position as distance to the ground, so of course, since the stone is falling towards the ground, that means it's moving in the negative direction compared to the positive direction we have chosen for measuring the position. Now finally, we would like to know how long it takes if instead of dropping the stone from the top of the tower, we throw it downward with an initial speed of 5 meters per second. So we proceed exactly the same way. We replace this dropped by an initial speed of 5 meters per second. All the rest is exactly the same calculations. Specifically, the velocity is the antiderivative of the acceleration, and the acceleration is only the acceleration from gravity, so we get the same form for the velocity. The only difference is that now, at time t equals 0, the velocity is not 0, because we don't just drop the stone, we throw it down. We throw it downwards, so that's in the negative direction, so the initial value of the velocity is negative 5 in meters per second. And that means c has to be negative 5, so that means the velocity function is negative 9.8 t minus 5. Now this is the rate of change of position, so the position is now an antiderivative of the velocity. So that gives us negative 4.9 t squared minus 5t up to some constant. To get this constant, we look at the initial position. At time t equals 0, we are at the top of the tower, so 450 meters above ground. That means S of 0 is 450, and it is also d, so d has to be 450. That gives us the distance to the ground at time t, that is given by 450 minus 5t minus 4.9 t squared. That's measured in meter, where time is measured in seconds. So now that we have the position function, we want to know when the stone reaches the ground. It's going to reach the ground if the position, which is distance to the ground, is equal to 0. So we set this new position function equal to 0, and that gives us a quadratic equation in t. We can solve it, for instance, using the quadratic formula, and we get formally 2 possible times. However, you see that under the square root we have something strictly greater than 25, so if I pick the negative sign, I would get negative 5 minus something positive, and in any case we would get a negative time. So the only positive time, the only positive solution is negative 5 plus square root of 25 plus 4 times 450 plus, times 4.9. That is negative 5 plus the root of 845, all this divided by 9.8. That gives us a time of approximately 9.1 seconds. That means the stone hits the ground approximately 9.1 seconds after it was thrown down. Remember that if we just dropped the stone, it was 9.6 seconds approximately. Okay, now it is time for you to turn to homework before you turn to the review quiz and the quiz.